Hello, yes. Myself, Dr. KSR Radhika, working as Associate Professor in the Department of Computer Science and Engineering, SRKR Engineering College, Bhimvaram. So, in this session, I'm going to explain about the different software architectures that are appropriate for different embedded systems. So first of all, in this session, I'm going to tell you about what is the need of different software architectures, and next I'm going to explain about the simple architecture, that is round robin architecture. So first of all, the objectives of today's lecture is to understand about the round robin architecture. So first of all, we will see the introduction for software architectures. Software is normally designed to accomplish a task in an efficient manner. So the primary concern about the design of software in the embedded systems is to obtain greatest amount of control over system response. The systems that require little control and poor response can be done with simple architectures. And suppose if for complex systems, that is for rapid response systems, so the design must be somewhat complicated. So that is whenever if you depending upon the application, so you have to choose the software architecture for the embedded systems. So now so whenever you are designing an embedded system, so the main thing first of all you have to consider is which architecture will be most appropriate for our embedded systems. So and also you should also know how much control you need to have the overall system response. Suppose if you want the good response, so the good response depends upon the absolute response time, the speed of the microprocessor, and other processing requirements. So and suppose whenever if you are considering the embedded system, so how the system must respond, so it should respond to different events, and also it should also check about the various processing requirements, and also it should consider the different deadlines for the different tasks or different interrupt routines, and also it should also consider about the system should also respond with different priorities. So considering all these requirements, so whenever we are designing an embedded systems, so selecting a suitable and appropriate software is the first important thing we have to check it. So whenever we are considering the software architectures, so we have different types of software architectures for embedded systems. The different software architectures. So here we have four different types of software architectures. The first one is round robin architecture, and which is the simplest one. And next one is round robin with interrupts, and the function queue scheduling architecture, and the last one is the real-time operating system, which is mainly used for most complex architectures. So in this session, we are going to see about round robin architecture, which is the simplest one. So considering the round robin architecture, this is the simplest imaginable architecture. So here, whenever we want to use this round robin architecture, so it is a very simple one. So and also it is very attractive for simple environments. So whenever here if you consider, so here we can say that here the main loop mainly checks each of the IO devices in turn and services any that needs the service. So and one more important point here we have to consider is, so it doesn't have, so that means here we don't have any interrupts, and here we don't have any shared data. So suppose if you don't have the shared data, then automatically you don't have the shared data problem, and also no latency concerns also here. So latency is limited by the maximum duration of the loop cycle. So how much time the loop cycle takes, that itself will be the latency. So this is very simple architecture for simple embedded system applications. So suppose if you consider the software routine for the round robin architecture. So if you see here, just we have a main loop. So in this main loop, so suppose if you have the devices, for example, in this example here we have seen that, so it has the devices from A, B, C up to we have Z devices. So that means what, here it has to provide services to all the 26 IO devices. So that's why what we have to do is everything should be given in the continuous loop. And here what we will do is just we will, for each and every device, we will check if IO device A needs service. So that means what? Suppose if the IO device puts a request that now it requires a service, then it puts a request. So then what happens is, so that means if it puts a request, then this condition will be true. And what happens? So what happens here? The control is given to the IO device. So take care of IO device A. So then what happens? So once the control is given to the IO device A, so then whatever service is required by the IO device, that will be handled here. So handle the data to or from IO device A. Similarly, all the other devices. So the next condition is for IO device B. So if IO device B needs the service, so what happens? Take care of the IO device B. So that means what, if this condition is true, then the control will come to the, that is the control will come to the IO device B. So once the control has been come to the IO device B, then you can handle the data to or from the IO device. Similarly, for each and every device, so like this, you have to provide for all the devices that are connected to this one. So that means here how many devices we have? So we have the devices from A to totally up to Z. So that's why here, so for A you have written. Similarly, you should also return the service. So here you have to, in this, so here just it is given as comments. So here what you have to do, you have to give the code depending upon your application. So so here for device A it has been given, next for device B it has been given, similarly C, D, E up to, so finally the device Z. So if IO device Z needs the service, so if this is true, again take care of IO device Z and then handle the data to and from IO device. So that means that the Z also, now here it will handle the necessary service that is required by the device Z. Okay, so this is how you can write the simple software routine for round robin architecture. So in this loop, if you observe, in this loop, if you observe, so all the devices have been provided here. Suppose if you check, so if you check here, so the time will be, so for example, if suppose if A needs the service, so the service will be given for A, then B, so on like that. So like this, the services will be given for each and every IO devices that are being connected for you. So this is the simple software routine for round robin architecture. So so now we will see a simple example, that is digital multimeter. So where this round robin architecture has been used. So here this is a simple digital multimeter. It measures the electrical resistance. It measures the current. It measures the potential in units of ohms, amps, and volts. Okay, each in different ranges. So if you observe here, so in this diagram, so you can see, so it is measuring the electrical resistance, and it is measuring uh, the current and also the potential. So here also the units are also have been given as ohms, amps, and volts. So here if you see, the range is given 1, 10, 100. Similarly for volts also it is given as 1, 10, 100. So this is the different ranges. So whatever range you want, so you can fix at that range. Okay. So here the digital multimeter has two probes. It has two probes that user touches to the 2 points on the circuit to be measured. So wherever, so if you see this These are the two probes. So wherever on the circuit, wherever you want to measure, so you have to touch these two probes at that 2 points. So once it has been touched, then you have a digital display. So you have a digital display. So where whenever the two probes touches the circuit, so that particular, for example, if you want the resistance means electrical resistance means the electrical resistance will be displayed. So here the current or potential anything, so whatever it has been touched on your circuit, that particular value will be displayed on this digital display. And also if you observe here, so you also have a rotatory switch. So this is a rotatory switch for which it is used for it is used for selecting the measurement range. So you can turn this switch and you can select the measurement range. So this digital multimeter makes continuous measurements and changes the display to reflect the most recent measurement. Suppose, so here this value will be changed, this value will be continuously measuring the value, and this value will be changing. So at each and every point, it changes the display to reflect the most recent measurement. So you will have the ups and downs, so that most recent measurement will be displayed here. Okay, so this is how you can find the you can measure the electrical resistance, current, potential in the corresponding units in different ranges in your circuit. So this is how you can get the measurement. So this is a simple digital multimeter which uses the round robin architecture. Now we will see how this is how the software routine is implemented for this particular embedded system, that is this digital multimeter. So this is the pseudo code for the digital multimeter. So suppose if you observe here, so here first of all we have given void v digital multimeter, so main. So here we are giving enum. So enum is enumerated data type, that is user defined data type. So here we are giving the ranges, that is 1, 10, 20 like that. So this e switch position is an enumerated variable. So in the while loop, so this is the continuous loop where we have to specify we have to specify whatever that is to be done in this particular system. So here what we are giving, so first of all we are giving in the continuous loop, we are giving the different cases, that is, so here e switch position. So first of all what we are doing here, we are reading the position of the switch. So we are reading the position of the switch. So once we are reading the position of the switch, so then it is given in switch case, that is, suppose if it is ohms 1, so read hardware to measure ohms. So and then what it is doing, so one more thing we have to do is we have to format the result and then break. Suppose if it is another case, that is if the range is ohms 10, so then we will read the hardware measure to measure the ohms in this range, and you will format the result and break. So on like that. So how many cases you have, that many cases you can specify here depending upon your application. And finally, once the loop is closed, so that means your continuous loop is this while true is closed here. So once, that means what, once this loop if it is ended for example for one time, then we can say that it has read some value. So then what it has to do, it has to write the display, it has to write the result to the display. So this is how it will read the temperature, read the current or resistance. So it will read it and it will display it on this digital. It will display it on this digital display. So first, what it will do is just it will check the position of the rotatory switch, and then makes the appropriate measurements, formats its results, and finally it writes the result to the display. So this is what we have written in this pseudocode. So this round robin architecture works well for for this system, because this is a very simple system, because here we have totally how many IO devices? Here we have only 3 IO devices. So, and also whenever if you consider here, whatever processing we are doing here, the processing. So here not, the processing is very simple. That is no particular, so we don't have any particular lengthy processing, very simple processing. So just read hardware to measure the ohms, and finally just we are formatting the result, that's all. And also here no tight response requirements, because suppose if the display is somewhat late also, we don't have any problem. So that's why here we don't have the constraint of very tight response requirements or something like that. So that's why here there is no problem with the response also. So that's why here in this particular application, that is digital multimeter, the round robin architecture is an adequate to meet all these requirements. So that's why you can use round robin architecture in this particular application as the architecture, software architecture. So whenever we are considering this round robin architecture, so here there is one worst case, that is, suppose if any one device needs response in less time than it takes the microprocessor to get around the loop. So then we have the problem. That is, for example, if A and B, for example, if A and B takes 5 milliseconds, then processor won't always get to the device Z quickly. So that means because first the device A has been given in your loop. If you observe here, so first the device A has been given, and next the device B, and finally the device Z. But here what is our main aim is, so the device Z requires, for example, if it requires in 3 seconds, in 3 milliseconds. So then what happens if A requires 5 seconds and B requires 5 seconds, and then for example, if you have Z, so then what happens? It requires 5 seconds. So it takes 5 seconds, 5 milliseconds, sorry. And this takes 5 milliseconds. So totally how much? 10 milliseconds. So that means what? The Z has to wait for 10 milliseconds. So instead of writing in the same order, in such a type of cases, so this is somewhat some the worst case scenario for round robin architecture. So in such a type of situations, what you can do is you can change the order. So you can change the order, because here A is somewhat some urgent service. So then what you can do, you can change the order, and you can write the order as, so first you can write the A, and then you can write the Z. So that means what? So the Z will get the service after 5 milliseconds, because here after A, Z has been given. So then what happens? So the Z has to wait only for 5 milliseconds. So once the A has been completed in 5 milliseconds, then the service will be given for Z. And then again you can give the service for B. So again B will take for 5 milliseconds. So then again you can write the Z service. So that means what? In this loop, you can write it as A, and next you can give for Z, and next you can give for B, and next you can give for Z. So like this, depending upon the requirement of our application, you can change the order, and you can provide the urgent services also for your application. Okay, so this is one point you have to consider whenever you are using the round robin architecture. And another one is, if none of the required response times are absolute deadlines, system may not work well if there is any lengthy processing. So that means what? For example, the response times are the absolute deadlines. So whatever response time that is given, that itself is the absolute deadlines. So then what happens is, so it may not work well. When suppose if there is one particular task that is so much lengthy, so that is it takes more time, lengthy processing. So in digital multimeter, For example, if you take, if some case takes 3 milliseconds, if some case takes 3 milliseconds, then the system's response gets as bad as 3 milliseconds. So that means what? Here, for example, here that is a lengthy processing. So then definitely the system's response will get bad as 3 milliseconds. That is one point you have to consider for round robin architecture. And also we say that this architecture is fragile. Okay, some suppose, that is for example, some device or its requirements may break everything. So in that case, so we say that it is fragile. So, and also we can say that this architecture is suitable for simple devices like your digital multimeter, digital watches, etc. So this is how you can use the round robin architecture for your simple embedded system applications. So finally, in this session, we have seen what is the need of the how you can select the software architecture for embedded system, and also we have seen in detail about the round robin architecture. Thank you all. So if you like my video, please like, share and subscribe to my channel.